In this video, we're going to look at a few exam questions that are all on the same topic, area under curves, using integration. So there's a few things we might spot to start with about similarities between these questions. Firstly, they all involve polynomials. We've got cubic equations in questions 1, 2, and 3. We've got a quadratic and a straight line in question 4. When you get to year 2 A-level maths, you will be able to apply the same general principles here to more sophisticated functions. You'll learn how to integrate trig functions, exponentials, etc. For now, you will expect to see polynomials, and we have rules for integrating polynomials that we can follow. So the process of integration, like in the very first question, part I, shouldn't be too daunting to you. The subtleties for questions like this come into how we calculate an area in each of these different situations. I've chosen these 4 questions partly because they have diagrams shown so we can visually see what's different about them. The first question is calculating an area where the curve is all above the x-axis. The second question, the curve area is entirely below the x-axis. The third question is where we're looking at the area between 2 points where the curve crosses in between, which means some of the area is above and some is below. And the last one is the area of the curve, the area between a curve and a line which is not the x-axis. So that's going to present some slightly different challenges to us. All right, let's dive in and look at the first question. We'll see the solutions in their most simplified, efficient form on the right, but we're going to talk through them a little bit so we can understand the detail and perhaps where the marks come from. Bear in mind the marking allocation may be a bit different with the new spec exam questions. Quite a lot of these are taken from old spec, so don't expect necessarily to get exactly the same number of marks for a question like this. That very first part, integrating the cubic, we are following the standard result. So we've got a standard formula. The integral of x to the n is x to the n plus 1 divided by n plus 1. And the only proviso we need is that n is not equal to -1. So this won't work for 1 over x, but in fact it will work for all sorts of other values. So x to the half, if you need to integrate the square root of x, you can use this result for it. That's essentially what they're testing on for this first part. You can see that x cubed has become x to the 4 over 4. Minus 3x squared becomes minus 3x cubed over 3, and the 3's cancel out. Minus 6x becomes minus 6x squared over 2, which simplifies to minus 3x squared. And don't forget the constant. Technically, if you've got 8, it's the same as 8x to the 0, which integrates to 8x to the power of 0 plus 1 divided by 1. So that just gives us 8x. And if you get into a muddle with this, remember you can differentiate your answer. See if it gets you back what you were trying to integrate. So if you try differentiating 8x, you should get an answer of 8, and that'll convince you you've done that right. Differentiate minus 3x squared, you'll get minus 6x, and so on. The only other thing to notice is don't forget the plus c. It's a very common mistake to make, especially when it's a standalone question. You're not going to go on to use it later. A lot of the places where you're likely to lose marks for forgetting plus c, and particularly with new spec questions, is when the subsequent parts of a question require you to calculate the value of c and then use it. And if you've missed it off entirely, you might get in a muddle and not know why your answers are not working the way they should. You won't always lose a mark for missing off the plus c, because it's one of those things that's kind of, technically, we all know that if you integrate something and you construct an indefinite integral like this one is, there's no definite value for it, it's an expression, then we will have a constant of integration. And unless we provide any additional information, like, oh, this particular thing has an area of this between these values or something like that, you're not necessarily going to be able to find the value of c. But we still need to make sure we include it, because it will affect the validity of our answers. There's an entire family of curves that would differentiate to give x cubed minus 3x squared minus 6x plus 8. Now for the second part of this question, we're looking at definite integration. They've asked for the area of the shaded region, which means we need to look at the limits. If they hadn't helpfully given us the -2 and the 1, we would have needed to calculate those by, well, I suppose you could put that cubic into your calculator. Remember, your calculator has got the capacity to deal with cubics. You just need to go to option A and choose polynomial of degree 3. We could put in the 1, the -3, the -6, and the 8. And now we've got our roots, -2, 4, apparently that's the value of b, and 1. So that's going to be helpful. The cubic calculator won't do quite as much as the quadratic one will. It won't give you the stationary points. But we can tell, for instance, on this graph, the value of a straight away, because that's the point where the curve crosses the y-axis. That happens when x is 0. So we get y equals nothing, take away nothing, plus 8. So a must be 8. Or if we're treating a as the point, a is the point with coordinates 0, 8. That might be helpful in a moment when we're trying to check our answer for the area of the shaded region. So to do this, notice it uses the word hence. That means we need to make use of our previous result, but that shouldn't come as any surprise. The way we find areas is by integrating. Remember that integrating effectively adds up for us the area of an infinite number of infinitesimally small rectangles between one value of x and another one. We always put the leftmost value of x as the lower limit in our integral and the rightmost value as the upper limit. If we do it the other way around, we get the exact negative result. And for this one, because the curve is above the axis for the entirety of the region, we're expecting to get a positive result for the integral. Not only that, but that positive result will exactly correspond to the area. Think of it in terms of something which is always moving forwards. If you calculate the total displacement, that will be the same as the total distance. We'll see how that changes with the later questions, where perhaps it's always moving backwards, or it's moving forwards and then backwards for a bit. Distance and displacement are not always the same thing. Once you've got an answer for this part, we can substitute in values 1 and -2. We put the 1 in first, and then we put in 2, and we subtract 1 from the other. One thing you might notice is that C doesn't appear in this bracket. That's not because we've forgotten it so much as we don't need it. If there was a C, even though we didn't know its value, it wouldn't matter. There will be a plus C in this bracket, there'll be a plus C in this bracket, and when you subtract one bracket from the other, C take away C is 0, so it would disappear anyway. So we can safely ignore it if we're doing definite integration. Now, it's a good idea, even if you don't write this out in full, to be aware of what happens when you square or cube negative numbers. Watch out for this. A very common mistake would be something like this. If you're trying to cube, let's say, -4, you might type -4 to the power 3, and it's no surprise we get an answer of -64. That is -4 times -4 times -4. But if you try -4 squared, somehow it always also gives you a negative, -16. That can't be right. The reason is the calculator is following the laws of the order of operations, and it's saying that you want to square the number 4 and then put a minus sign in front. If what you really want to do is square the number -4, you have to make sure you put it in a bracket. So whether you rely on the calculator or not, be careful with your negative signs when you're subbing numbers in. And when you've got your answer, you can check that it makes sense, because A, we're expecting a positive value, and B, we have a rough idea from the value of A that we've identified how big this should be. If the height there is 8, then it looks like the overall height of the curve is, I don't know, maybe 10, something like that, 9 or 10, possibly more. And we've got the width. So if we treat this as if it was a triangle, we could very quickly come up with an estimate for the area of that shape. So if we say it has a width of 3, which it does, and a height of 10, which it probably doesn't, but that's close enough, then we would have an area of the triangle being 3 times 10 divided by 2. That gives 15. We've got a slightly bigger number. Well, probably because it's actually slightly higher, but also because it's curved, it's bowed out from where the triangle would be. So a triangle is always going to give you an underestimate for this, even if you find the exact value of the stationary point. 15 is not that far away from 20.25 when it comes to a rough and ready estimate like this. And it's encouraging that we can get a quick answer just by using very quick mental maths on the curve that we can see. Moving on to question 2. With question 2, we have an area under the curve. Apart from that, a lot of this is very similar. They've asked you to integrate this cubic expression between -1 and 3. So this is now a 5-mark question because it's not enough just to calculate the indefinite integral. We've got to integrate these terms and then substitute in the -1 and the 3. Put in 3, put in -1, take 1 away from the other and see what you end up with. Be careful with your negative signs. We get an exact value of -32. And we are expecting -32. If you write 32 for this one, that will not be correct. The reason is this is underneath the axis. So if you remember how integration works, adding up the area of all the infinitely thin rectangles, these rectangles have technically a negative height. Because we're using y as the height of each rectangle, the y value is negative for these ones, so it's going to give a negative total area. That's not necessarily a problem. It's like asking how far north you've driven, and you say, I've driven north -32 miles because I've been going south. I can still use that information to calculate how far you've gone, provided you've always been going in the same direction. So that's what I've used here. This general pattern we can follow. The area is going to be the size of the integral, provided the integral is always above or always below the axis. The area is given by the size of the integral, provided it is entirely above or entirely below the x-axis. If it's a bit of each, it's a bit like traveling 10 miles north and 3 miles south. You've gone you're 7 miles away from where you started, but you've done 13 miles of journey. So if you want to know the distance covered, that's different to the displacement in that case. Okay, let's look at the next question. Question 3 involves a little bit of positive and a little bit of negative area. Again, we've got a cubic expression, but the very first part of this question asks you to factorize it. Now, it's not as hard as it looks. In general, cubics are awkward to factorize, but this one has x as a factor, so we can pull out x straight away. And then we're left with a quadratic that can be easily factorized itself. So x times x plus 1 times x plus 3. One of the reasons they've asked you to do that is so that you can identify the coordinates, the points where the curve crosses the x-axis. There's the 0, here's the -1, here's the -3. And that's where part 2 comes in. All of that is, in fact, scaffolding. It's to help you with the next part of the question. Find the total area of the shaded region bounded by the curve and the x-axis. And to be honest, a new spec exam question might well just jump straight in at part 3 here and ask you for the total area. And it would expect you to recognize that you can either use the calculator or your own algebraic approach to find the roots of the curve and therefore recognize where you need to integrate. Now, this has to come in 2 parts. It's like the example we just talked about. If you travel 10 miles forwards and 3 miles backwards, then calculating your overall displacement leaves out the information about how far you've gone. If your direction changes along the way, in this case, the curve going below represents the point where now we're starting to add in a negative area. If the total positive area above the axis was 5, and the total negative area here comes out as -2, then if you integrate the entire thing, you'll get an answer of 3, 5 and -2 added together. If you want to find out the total area, ignoring the sign, you need to separately integrate both sections and then add the sizes of them together. And that's what's happening here. The first section above the x-axis, we need to integrate from -3, the leftmost root, to -1, the middle root. When we've done that, we should get a positive answer. And here we get 8/3. I'm going to leave it in its exact form. The second section is below the x-axis, and that should be between -1 and 0. So that's what's been done here. If we calculate that precisely, we get an answer of -5/12. And then if we want the total area, we have to positivize those numbers, essentially. We want the size of those two. So we're going to say the size of 8/3 is, of course, just 8/3. The size of 5/12 is 5/12, and the size of -5/12 is also 5/12. And when we add those together, we get 37/12. You could also check that this is sensible. If you wanted to try some numbers, you could, for instance, substitute in -2 to get a rough idea of how high this curve goes. and that might help you to get an estimate for the area. But depending on how much time you've got in an exam, it may not always be possible to spend that much time. The key thing to remember here is if you want the area between the curve and the x-axis, make sure you split the integral up into exclusively above and exclusively below regions. It may be necessary to solve an equation, for instance, in this case, finding the roots of that equation in order to do that. Right. Question 4. We have a quadratic curve, we have a straight line, and they've shown us that they intersect at the point 0, 5, which we could verify because we can see that y equals x squared minus 3x plus 5 has the same y-intercept as y equals x plus 5. And at another point B. They haven't told us the point B, but we can solve a simultaneous pair of equations where one's linear and one's quadratic. We just need to substitute the linear one into the quadratic one. So if y is x add 5 and y is x squared minus 3x add 5, then x add 5 is equal to x squared minus 3x add 5. When we sub that in, we can simplify the equation. We find our two solutions. One of them shouldn't surprise us. X equals 0 is the first solution. That's because they cross on the y-axis when x is 0. The other solution is the one we're interested in, x equals 4. So we see that the point we already know about, we've got coming out of our simultaneous equations. That encourages us that we've done it correctly, we've not made any mistakes. And then the other point must therefore correspond to the other point where the two curves cross, where the quadratic and the line cross. The second part asks you for an indefinite integral. In other words, we haven't given you any limits, there's no numbers to put in, you should get something plus c. And in fact, before you even begin, you should have some idea of what it's going to be. If you integrate a quadratic, you'll get a cubic expression, and there'll be a constant on the end. So x squared becomes x cubed over 3, minus 3x becomes minus 3x squared over 2. The 5, remember, becomes 5x, because 5 is the same as 5x to the 0. And finally, we have a constant on the end because that would differentiate to 0. That's the information that's been lost. Now, for the third part, the area between the curve and the line, we have to remember what it is that integration does for us. Integration will give you the area bounded by the curve and the x-axis between 2 points. And if the curve is below the x-axis, it comes out negative. But if it's above the x-axis, it'll come out positive. Now, what's really happening here, therefore, is that the area underneath the curve, once calculating, so if we go from x equals 0 to x equals 4, the x-coordinate of b, we're going to get this area enclosed by the curve, the y-axis, the x-axis, and the line x equals 4. In other words, it's what's left over when we cut r out of the trapezium made from A and B and the vertical from B. So we can calculate that area, but we need to do it in the same way you would have done a compound area problem in GCSE. So we find the area of the entire shape. That's the area under the line. You can do that in a few ways, but probably the simplest way is by recognizing that you're looking at a trapezium. Or alternatively, if you're less comfortable with the trapezium formula, by breaking it into a rectangle and a triangle. The point A has coordinates 0, 5. The point B has coordinates 4, 9. We can use that to work out the height OA and OB. That's effectively the widths of our trapezium. So you can get the average width by doing 5 add 9 divided by 2, multiplied by the height, which in this case is horizontal, between A and B, which is 4. And that should give you an area for the trapezium of 28. An alternative approach here is to integrate the line. If you integrate the line between 0 and 4, you'll end up with exactly the same thing. The integral of x add 5 is x squared over 2 plus 5x. You could substitute in the values of 4 and 0 and evaluate that, and you would get the same thing. Once you've got the area under the line, you then need to subtract from it the area under the curve. And what I recommend with questions like this, especially as they get more complicated, is that you write down what you intend to do before you dive in and get stuck into the algebra. That way you won't lose track of what you're trying to do. You won't forget what your numbers were going to be used for. I've found the area under the line. I find the area under the curve using integration between 0 and 4. So I sub in 4, I sub in 0, and I've got a value at the end for the area under the curve. One thing I should check here is that value, 52/3, is in fact smaller than the area under the line, which is 28. Turns out it is. Roughly speaking, 52/3 is going to be something like, I think, 17 1/3. So we can see that the area we've calculated through integrating the curve is less than the total area of the whole trapezium, which is encouraging. It's roughly half the size, but not quite. So when we find the area of the shaded region, we just subtract one from the other. And again, we can check that looks like a sensible number. 32/3 is about 10 or 11. So we've got a rough idea of how big that shaded space is compared to, for instance, the non-shaded section under the curve. If you need to, it's not a bad idea to annotate your diagrams, to draw on the extra lines, mark on the heights, mark on the values of the coordinates, anything that you can there to help you get a good read on exactly what's going on and to check that your answers make sense.